Okay, so let's quickly remind ourselves where we are in our story of scattering theory. So we are discussing scattering from potentials that have rotational symmetry. Okay, so then our ansatz for the wave function is given by the first line in the slide. You see, psi of r we wrote is e to the ikz, okay, which of course is the incoming plane wave, plus f of theta e to the ikr over r. And we justified this ikr over r by claiming that we are looking for solutions at regions far away from the potential, right? Basically are going to infinity region, asymptotic regions. And in this region, if you solve the Schrodinger equation, the radial wave function is going to simply give you the e to the ikr over r form, which is a spherical wave, okay? And multiplied by what is called a scattering amplitude f of theta, okay? So the goal of scattering theory is basically to compute what this f of theta is, because as we have seen in a previous lecture, the scattering amplitude f of theta is actually related to the differential cross section also. So once knowing f of theta, we know everything about the scattered wave. And of course, I should also mention that this is only true in the asymptotic region. So for example, in regions very close to where the potential is, the wave function can be modified non-trivially, and we are not claiming that this solution is valid in those regions. The next step was, of course, to recognize that we have all the angular information packaged in the incoming z, which is r cosine theta and the f of theta. And since any function of angles, theta can be written as an expansion in the Legendre polynomials, because PL of cosine theta form a perfectly respectable basis for functions of theta. We went ahead and did that. We wrote e to the ikz as a linear combination of the Legendre polynomials, and we wrote f of theta as a linear combination of the Legendre polynomials. And once you do this decomposition, your wave function looks like the boxed equation that you see here. And this is where we ended things last time. Okay, so I want to continue at this point, but I want to repackage this exact same information in the language of scattering matrix. Okay, and I want to motivate to you that this coefficient that you see in terms of the outgoing spherical wave e to the ikr over r is nothing but the elements of the scattering matrix. Now to do that, it's essential to remind ourselves what the S matrix is. And we did this last semester in a couple of lectures, but I'm going to redo this calculation at least to serve as a quick review of 1D scattering and to remind yourselves and ourselves actually what the S matrix represents and what is the S matrix all about. Okay, so today we will spend some time in a quick review of one-dimensional scattering. Okay, now to set the stage, I'm going to establish some notations, and my notations are going to be that I'm going to call any wave of the form e to the ikz as a right moving wave. And I'm going to call, sorry, R, and I'm going to have any, if I have a form e to the minus ikz or ikx, if I work in x dimension, minus ikx, this is a left moving wave. Okay. Now this of course is an abuse of notation, because ikx doesn't really tell you anything about which way the wave is traveling. And to know that, of course, you have to put in the time dependence, right? So suppose, what is the time dependence? The time dependence, of course, is e to the minus iet over h bar. So if I put in the e to the minus iet over h bar and recognize that I'm looking at scattering solutions, these guys are basically, in the asymptotic regions, these are basically free waves, right? So they only have a kinetic energy. They have no potentials, because I'm looking at the x going to plus minus infinity regions. So put everything in. For example, the e to the ikx now becomes, with the time dependence tagged on, this becomes e to the minus I h bar square k square t over 2m, and there is another factor of h bar. So this becomes e to the ikx times e to the minus I h bar k over 2m times t and another factor of k. Okay, and I can simplify this guy by writing this as e to the ik times x minus h bar k over 2m times t, and this has the right dimensions of velocity, so I can write this as e to the ik times x minus vt, which represents a wave traveling to the right with a velocity v, which is given by h bar k over 2m. And remind yourselves from the free particle lectures last semester why this factor of 1/2 comes into play in the velocity. Okay, so essentially the difference between phase velocity and group velocity. And of course, if I have an e to the minus ikx, this is going to give me a wave of the form e to the minus ik times x plus vt. And this is basically a wave traveling to the left with a velocity v. Okay, so in order not to keep tagging on the time dependence every time, I'm going to invent a shorthand wherein I'm going to call e to the ikx, because the right moving wave has an e to the ikx factor as a right moving wave, and a left moving wave as e to the minus ikx, because that is the kind of forms that we see here. Okay, so let us look at a very simple picture of scattering from the left, which means initially we're going to throw a particle from the left and the scattering center is somewhere over here. So I'm going to draw a non-zero region. This is v non equals 0, and everywhere else the particle is basically free. Okay, now since it is approaching the target from the left, it is going to come in this fashion. Okay, now it's going to interact with the region where v is not equal to 0, and it's going to be scattered to regions where the potential is equal to 0. So what will be the asymptotic form of this wave function? I'm going to call this psi r, because even the scattering is from the left, but the wave is traveling towards the right. This has the form, and this is the x is equal to minus infinity region, and this is the x is equal to plus infinity region. Okay, so I can always choose a scattering center to be around x is equal to 0 region. Now, the form of the wave is going to be such that the asymptotic form of the wave is going to be such that at x is equal to minus infinity, you're going to be seeing a wave traveling to the right. This is the wave, this is the particle that you put in initially, right? And then there is going to be some amount of reflected wave. Okay. Now, the reflected wave also has the same momentum k because of energy conservation, because it's going to come in with some kinetic energy h bar square k square over 2m, and it's going to go back far enough away from the potential. It is still going to be a free wave with the exact same kinetic energy h bar square k square over 2m. Okay, this will be the story, and the x is equal to x tending to minus infinity region. In the x tending to plus infinity region, of course, you're going to see a transmitted wave, which I'm going to call this e to the ikx. Okay, so r, little r is the reflection coefficient, and little t is the transmission. Little r is the reflection amplitude, and little t is the transmission amplitude. And the reflection coefficient capital R is modulus little r square, and the transmission coefficient little capital T is, so capital R is modulus r square, capital T is modulus t squared, and as you know, for conservation of probability, r plus t has to be equal to. Okay, so this is all stuff that you have seen before. So this is the picture when I scatter things from the left. Okay, let me underline this stuff. Now, what happens if I throw the particle from the right instead of the left? So scattering from the right. Well, the picture stays almost the same, except that now I'm throwing the particle from the x is equal to plus infinity region. So I have a non-zero region. So I have a region where the potential is non-zero, v not equal to 0, and in this region again v is equal to 0. Now I'm throwing the particle like this. Okay, So I'm throwing the particle from the right. It is moving towards the left in right towards the scattering region. So what is the asymptotic form of the wave function in this case? In this case, I'm going to call this psi L because the scattering is from the right, which means my incoming particle is left moving. Now this is of course the x is equal to minus infinity region, and this is the x is equal to plus infinity region. So what should be the form of the wave function, asymptotic form of the wave function? Well, at x is equal to minus infinity, I'm going to be seeing a wave traveling towards the left, which is the wave that I threw in, which is the particle that I threw in. So this is e to the minus ikx because it is traveling towards the left. And I'm going to be seeing a small amount of reflected wave traveling to the right. So I'm going to call this reflection coefficient r prime. And right, this is r prime e to the ikx. Again, I'm using the same k because I'm looking at regions very, very far away from the potential. So the wave is essentially free and it has to go out with the same kinetic energy it came in with. In the x is equal to plus infinity region, of course, now I'm going to be seeing a transmitted wave that is traveling towards the left. So I'm going to call that transmission coefficient some t prime e to the minus ikx. Okay, so this is in the minus infinity and this is the plus infinity. So far, so good. Are there any questions about any of this? Now, yes.
In the figure, shouldn't plus and minus infinity be opposite?
Yes, they should be opposite. Thank you very much. Sorry. I quickly changed it. So this is minus infinity, this is plus infinity. Here I've done it correctly. Anything else? Thank you. Now, you might actually wonder why we have to do it both times. Suppose if the potential cannot say left from right, for example, there should really be no difference, right? Whether I throw things from the right or throw things from the left. In other words, the reflection and transmission coefficients that I computed throwing things from the left should be the same or almost the same as the things that I threw from the right. Okay, so this is what your rough intuition should be, because it really doesn't matter if I'm standing to the left and throwing a particle or if I'm standing to the right and throwing a particle, because what is going to matter is, of course, the way the particle interacts with the potential is going to be the exact same, even if it approaches the scattering center from the left or the right. Okay, so this intuition turns out to be correct, and we can mathematically verify this by recognizing that one of these forms can be brought to look like the other form. So in other words, what I'm going to be basically claiming is this. Look, ultimately you're solving the Schrodinger equation and my potential is a real function. V of x is real, right? So this is important. Real function, and I am solving the Schrodinger equation, right? Minus h bar square over 2m d square psi dx square plus v of x psi is E psi, right? Now, if psi is a solution, psi star should also be a solution, right? I can take the complex conjugate of this entire equation and it still be true because v of x doesn't change because it's a real function. So see, if psi is a solution, psi star is also a solution, which is something that is trivial that you know. So, and the Schrodinger equation is also a linear equation. So if psi is a solution and psi star is a solution, then any linear combination of psi and psi star is also a solution, right? So if psi is a solution, psi star is also a solution. And since the Schrodinger equation is linear, a linear combination of psi and psi star is also a solution. So specifically, I will claim that if psi r is a solution, then I can also form the combination psi r star minus r star psi r. This is a linear combination of psi r star and psi r, which is of course a solution of the Schrodinger equation. So let me understand what the form of this particular linear combination of psi r star and r star psi r looks like in the x is equal to minus infinity and plus infinity regions. Well, in the minus infinity region, psi r goes like e to the ikx plus r e to the minus ikx. So psi r star should go like e to the minus ikx plus r star e to the ikx, right? Minus r star psi, psi goes like e to the ikx plus r e to the minus ikx. This is a story in x is equal to minus infinity region. In the x is equal to plus infinity region, psi r goes like t e to the ikx. So psi r star would be t star e to the minus ikx. And this guy would be r star t e to the ikx. Is this okay? So this particular linear combination of solutions has this asymptotic form. This can be further simplified because if you look at the x is equal to minus infinity, there is an r star e to the ikx with a plus sign and r star e to the ikx the minus sign. So these two cancel each other. So I can write this solution because this is the reason I chose r star over there. And if you take this particular combination, you will find that this is equal to e to the minus ikx minus mod r square e to the minus ikx, right? Which means I can further simplify this to write this as 1 minus mod r square e to the minus ikx in the region x going to minus infinity. Of course, in the region x going to plus infinity, no further simplifications are possible. So I will write this as t star e to the minus ikx minus r star t e to the ikx. Okay. So what have I done? Out of the solutions that I constructed for the scattering from the left, I constructed a particular linear combination. But if I look at this linear combination and I compare it to the scattering solution when I scatter things from the right, what does that look like? So I will again write this here. This is psi L, we just discussed, has the form r prime e to the ikx and t prime sorry, here I have the order switched, right? Because I made a mistake here. In the scattering from the right, psi L has the form e to the minus ikx plus r prime e to the ikx in the x is equal to plus infinity region. Okay, and it has this particular form in the x is equal to minus infinity region because this is where the transmitted wave goes. So this is the plus infinity region and t prime e to the minus ikx in the minus infinity region. So now let us look at the particular combination of the scattering from the right solutions and compare it to the scattering from the left solutions, and you see that they have an identical form. Psi r star minus r star psi r has the form something times e to the minus ikx in the minus infinity region. So does this guy. It has something times e to the minus ikx in the x is equal to minus infinity region. In the x is equal to plus infinity region, the psi r star minus r star psi r has the form t star e to the minus ikx. So something times e to the minus ikx plus something times e to the plus ikx, which is exactly what this guy also has. So one can now make a formal combination of these two guys. I can identify that it doesn't really matter if I throw things from the left or the right, as long as I make a connection between the reflected and transmitted coefficients in both these cases. What is this particular connection? Well, this connection is almost true, but not quite true. I have to do something else to do this. So if you actually look at this, and x is equal to plus infinity region, the psi L has only e to the minus ikx, okay? But the psi r star minus r star psi r has the form t star e to the minus ikx. So I'll have to divide things from by t star. So if I divide, so for example, psi L and 1 over t star psi r star minus r star psi r have exactly the same, excuse me, asymptotic forms. Now you might actually think, well, how can you possibly divide by something and then make the claim that they look the same? Is it not artificial? It is not artificial, because anyway we are dealing with wave functions that are not normalizable, right? So everything is defined only up to an overall constant. I can always absorb one factor of t star into the overall constant and divide this whole thing by a t star. Okay, so if I make this formal identification, then there emerges a relation between the reflected and transmitted coefficients of things going to the left and reflected and transmitted coefficients of things going to the right. What is this? Well, let us compare these two. So I'm comparing 1 over t star times 1 minus mod r square. This is the coefficient of e to the minus ikx, right? And this has to be t prime, because this is the coefficient of e to the minus ikx for psi L in the minus infinity region. In the plus infinity region, now that I've divided through by t star, psi r star minus r star psi r over t star has only e to the minus ikx, just like the psi L part. But since I've divided things by a t star, the coefficient of e to the ikx, this part, is minus r star t over t star. And this has to be formally identified with r prime, which is the coefficient of e to the ikx for the left moving part. Okay, so if I make this formal identifications, then I can find a relation between the reflected and transmitted coefficients in the two cases. And as you can guess, these bear a very, very similar form. For example, 1 minus r square is basically t square, right? So 1 minus r square, since r square plus t square is 1, this is basically t square, which is t star. So this first relation implies that t equals t prime. Okay, if you put everything in, 1 minus r square is t star, one factor of t star cancels, so t equals t prime. So the transmitted coefficient from scattering on the left and the right are exactly the same things. And if I again use this relation, this second guy simply means that, look, t over t star is just a phase, right? And minus is also just a phase. So r prime and r also differ by a phase. So r prime and r differ by a phase. In other words, if I calculate capital R, which is r square, it will be the exact same thing as r prime square, because little r and little r prime only differ by a phase. In other words, all this is telling us is that there is no fundamental difference between these two cases, provided you make these identifications, these very common sense identifications. And these two equations, which I will box, will become very important in the context of the scattering matrix, which we will come to in just a second. Okay, so this is stuff that we had quickly covered in the last semester, but I thought it's good to revisit this because I'm going to be using these definitions again in looking at this equation. So basically, I want to interpret this part. So that is my goal. So interpret this part, I have to go through all these examples. Okay. Now, it turns out that there is a more powerful and more elegant way to package information about scattering, and this has to do with S matrix. So there is an alternate way of packaging all the information about scattering in terms of the S matrix. Now, I'll first do this for one dimension, and you would actually quickly recognize that in one dimension, it is actually not a big deal. Because in one dimension, of course, everything that you need to know about scattering is codified in the reflected coefficient and the transmitted coefficient. If you understand these two coefficients, you know everything about 1D scattering. But the advantage of the S matrix is that it generalizes to higher dimensions very easily. In higher dimensions, you really don't calculate reflected and transmitted coefficients. You calculate other things called phase shifts and so on and so forth, which we will introduce. But the language of S matrix generalizes in a straightforward fashion. So that is why we still use this language. So what is this language? So to start with understanding what the scattering matrix is all about, we will define two ingoing wave functions, asymptotic wave functions. In other words, so if you look at this, look at these two pictures, you basically have two different kinds of waves, right? One that is going towards the potential, which I will call ingoing, and one that goes away from the potential, which I will call outgoing. Now, regardless of whether I do the scattering from the left or the right, there are ingoing waves and outgoing waves. For example, in the first case, scattering from the left, the ingoing wave is of the form e to the ikx, because that is the stuff that is going into the scattering center. The r e to the minus ikx represents an outgoing wave because it represents the part that is reflected back from the potential. Okay, so this is part of an outgoing wave. Similarly, the t e to the ikx can also be interpreted as an outgoing wave, but this time the outgoing wave is traveling towards the right. So in this particular example, I have one ingoing wave, which is a wave traveling in the right direction, and there's two outgoing waves, one traveling along the right and one traveling along the left. If I look at the scattering from the right picture, I have an ingoing wave that is traveling towards the left, towards the potential, right? This is the e to the minus ikx part. And there is again two outgoing waves, one traveling towards the right, which this is the r prime e to the ikx part, and one traveling to the left, which is the t prime e to the minus ikx part. So instead of formulating things as two different things scattering from the right or the left, I can think of both these cases in a common way in terms of ingoing stuff and outgoing stuff. So there is two kinds of ingoing wave functions. And I should caution that everything that I'm doing is in the asymptotic limit, right? Not close to the potential, but very, very far away. So in the ingoing, so let me erase this. Ingoing, there is a right moving ingoing, and there is, let me try to write it in a fashion that might be easier to understand. Ingoing, right moving, and left moving. Okay, what this means is that, suppose if this is the scattering center, a right moving ingoing wave goes like this. Okay, so this is of the form e to the ikx. A left moving ingoing wave approaches the scattering center from the left. So this is of the form e to the minus ikx. Ultimately, everything is e to the ikx or e to the minus ikx, but it depends on whether things are approaching the scattering center or moving away from the scattering center. Okay. So similarly, I can define two outgoing waves. Again, there is a right moving outgoing wave and a left moving outgoing wave. What does this mean? This means that a right moving outgoing wave is saying goodbye to the potential and moving towards the right like this. And a left moving outgoing wave is saying goodbye to the potential and moving in this direction. Okay. Now, in terms of the ingoing and the outgoing waves, I can define a column matrix and I can package all this information, these two asymptotic forms of the wave function, psi r and psi l, in terms of one matrix equation. The way I will do it is as follows. So to do this, I will again write psi r and psi l. I'll bore you by writing it again because it's easier for me to see what's going on. And psi l is okay. So if I write everything together, psi r, psi l, remember that psi r has one ingoing wave function along the right, which is the e to the ikx, and two outgoing wave functions from the left and the right. So I can write this. So I'll call this as IR, incoming right. This is incoming left. And this is outgoing right. And this is outgoing left. So the goal of scattering is to understand the ingoing wave functions in terms of the outgoing wave function. So what fraction of the wave function is actually scattered? So that information is actually contained in the outgoing waves, not the ingoing waves, because ingoing waves is the stuff that you throw into the potential, right? So I can write this as IR, IL plus some stuff times OR, OL. Again, please understand what this equation means. There is nothing new here that is not already contained in these two equations, but it is simply a repackaging of this information in terms of ingoing and outgoing waves. The ingoing part of psi r is e to the ikx, right? And there is two outgoing waves. One because it is reflected and reflected away from the potential, and one that is transmitted through and moving away from the potential on the right. So the part that is multiplying OR, which is an outgoing wave traveling to the right, is T. So this is T. And the part, because T times OR is T times e to the ikx, as you can see, this is your OR. And of course, the part that is multiplying OL, which is the outgoing wave traveling to the left, is R. Similarly, in the psi L case, the incoming wave is a wave traveling to the left, which is e to the minus ikx, right? And then there is an outgoing wave to the right, which has a coefficient r prime, and an outgoing wave to the left that has a coefficient t prime. So I can write this as r prime and t prime. Is this clear to everybody? Are there any questions? If you write IR as e to the ikx and OR as e to the ikx, you will again get the exact same equation as above. Okay, but the essential difference between the matrix that you see and the two wave functions that you see on, above is that one makes a distinction between the two e to the ikx's. Okay, even though there are two waves that are traveling along the same direction with the same velocity, with the same momentum, there is one that is actually thrown into the potential and one that is actually transmitted through the potentials. They both have the exact same form, e to the ikx, and one makes a distinction between these two. Okay, so as you can easily guess, all the information about scattering is in this little 2x2 matrix. Okay, so I can write this again as psi r, psi l is just mostly the incident part, IR, IL, plus some stuff that is scattered and goes as outgoing waves. And all the information about the outgoing waves is packaged in this little matrix called S. And this is the famous S matrix. And in 1D, it has the form T, R, R prime and T. Okay. Now it has very, very nice features. We will explore how to write this S matrix, and for example, in the parity basis in a tutorial. But I will talk about one particularly important property of this S matrix, that is the fact that the S matrix is unitary. So let us actually explicitly demonstrate this. What is SS dagger? SS dagger is T, R, R prime, T prime. Remember that these are all quantum mechanical amplitudes, so all of them can be complex, right? So the dagger of this guy is T star, R prime star, R star, T prime star. So what is this equal to? This is equal to the 1 element is T star, which is mod T square, plus R star, which is mod R square. The 1 element is T R prime star plus R T prime star. The 2 element is this, and the 2 element, as you can easily check for yourself, is this. Okay. Now, since R square plus T square and R prime square plus T prime square are both equal to 1, it remains to understand what the off diagonal elements are. What are the off diagonal elements? This is T R prime star plus R T prime star, right? But we know how R prime and R are actually related to each other. T prime is the same as T, and R prime is minus R star T over T star. So let us use this information, and I can write this as, so I will write R prime in terms of R. So this is minus T. R prime star would be R T star over T, right? R T star over T plus R T prime star. Okay. Any questions about this? Since R prime is minus R star T over T star, R prime star would be minus R T star over T, right? So I will simply use this relation, and this basically is telling me that this is equal to minus R T star plus R T prime star. But I also know that T is equal to T prime. So this is equal to 0. Similarly, you can also show that the 2 element is also 0, and SS dagger is actually equal to 1 0 0 1, which tells you that the scattering matrix S matrix is a unitary matrix. And this has to do with probability conservation. The S matrix being unitary is always true, whether you're doing quantum mechanics in 1 dimension, quantum mechanics in 3 dimensions, quantum field theories in whatever dimensions. S matrix is always unitary. This has to do with probability conservation in quantum mechanics and particle number conservation, for example, when you do field theories. Okay, so this is a very important property of the S matrix. The S matrix again is the coefficient of the outgoing part of the scattering waves. So all the waves can be written as an incoming part and an outgoing part, and the coefficient of the outgoing part is basically the scattering matrix S. Okay. So this is exactly what I want you to understand from the discussion thus far. Again, we will explore a couple of properties of scattering matrix in 1 dimension, the tutorial problem. Now let us get back to our 3D problem. Get back to 3D. Okay, let us look at the wave function that we wrote down, which I will write again. I have it somewhere. So let me go back. What is this equation? So if I write this equation again, I have L equals 0 to infinity. This is again the asymptotic form. Just like in the 1D case, we've only looked at the asymptotic forms of the wave function. We're again looking at the asymptotic form of the wave function in 3 dimension, which is 2ik times minus 1 to the L plus 1. We have an e to the minus ik r over r plus 1 plus 2IFL e to the IKR over R, the whole thing times PL of cosine theta. Okay. So this is an incoming spherical wave, and this is an outgoing, not this, this is an outgoing spherical wave, which means that whatever is multiplying the outgoing wave has to be the scattering matrix. So the scattering matrix in this case is SL, is the coefficient of the outgoing part of the wave function, which is in this case 1 plus 2IFL. Okay. Because an exact analogy with the one dimension part, the definition of scattering matrix is basically all that is non-trivial happening is encoded in the outgoing wave functions. So the coefficient of the outgoing wave function is basically the elements of the scattering matrix. So in this case, the coefficients of the outgoing wave function is basically 1 plus 2IFL. So we write S with a little l because it depends on which L you're talking about. So this is of course an infinite sum with various different L's. And the scattering matrix is 1 plus 2IFL. And as you can easily see, for rotationally invariant potentials, a scattering matrix is basically a diagonal matrix. It has no off diagonal elements. It only has elements 2IFL. Okay, where L equals, of course, 0, 1, 2, blah, blah, blah. Okay. So far, so good. So if I have a diagonal matrix, which is a unitary matrix, then what should the diagonal elements be? Anybody? I have a diagonal matrix which is unitary. So what can you say about the diagonal elements?
Its eigenvalue 1 1.
What are the eigenvalues of a unitary matrix?
1 1.
Yeah, place. Right? In any dimension, if you have a unitary matrix, its eigenvalues are just a phase. So we can actually easily see this. For example, let's look at a 2 by 2 matrix, right? So we have a 2 by 2 matrix, let us say, with diagonal elements A, 0, 0, B. Okay. Now, what is A dagger? I want A dagger to be unity. So this is A0, 0, B times A star, 0, 0, B star, which is mod A square, 0, 0, mod B square. And I want this to be, which means I want the absolute square of every one of these elements to be 1, which tells me that A can be a pure phase. Okay. So the diagonal elements of this scattering matrix, so I'll erase this because this part is fairly straightforward and you guys can easily guess it. So I can write the elements of the scattering matrix SL as e to the 2I delta L. Now I should still carry the information about L because the diagonal elements are different for different values of L, and I will encode that in this delta L. Okay, and this is a pure phase, and the factor of 2 is chosen in terms of convention. There is nothing deep about that. The delta L are called phase shifts. So if I so basically what is happening, I'm throwing in a wave, right? And I'm decomposing this incoming wave in terms of all possible spherical wave with all possible values of angular momentum. I have a rotationally invariant potential that is doing the scattering for me. Since it is a rotationally invariant potential, if I throw a wave with L equal to 5, the outgoing wave is also going to have L equal to 5 because it is rotationally invariant. It cannot change the value of the angular momentum of the wave that I'm throwing in. So all the information about scattering is basically contained in the delta L, which is a phase shift. Okay, so I'll have to compute the phase shifts. So I'll have to set up a machinery to calculate these phase shifts. So before I do that, let us look at the scattering amplitude, which, excuse me, f of theta. We wrote f of theta as a linear combination of the PL of cosine theta in this particular fashion, right? So what is my FL now? So 1 plus 2I FL is basically a pure phase, which I'm writing as 2I delta L, which tells me there is two different ways I can write FL. They are both mathematically equivalent. FL can be written as 1 over 2I times e to the, 2I delta L minus 1, right? If I pull out a factor of e to the I delta L from this guy, I can write this as e to the I delta L times e to the I delta L minus e to the minus I delta L over 2I. So FL can also be written as e to the I delta L times sine delta L. Okay, because basically the parenthesis is sine delta L, definition of sine theta. So using this definition of FL, I can write my scattering amplitude f of theta as 1 over 2ik, either one of these definitions, 2L plus 1 times e to the 2I delta L minus 1 PL of cosine theta. Okay. So the goal of scattering theory in quantum mechanics is to calculate the scattering amplitude. And to calculate the scattering amplitudes, we need to figure out what the phase shifts are, delta L. Now, on the looks of it, this looks like an impossible problem because there's an infinite number of L's and we have to find an infinite number of phase shifts. But we'll actually see that in all practical problems, the ones that are modified most by most of the typical scattering potentials are low-lying L's, so L equal to 0 and 1 mostly. So you only need to compute a finite number of phase shifts. And once we compute the phase shifts, we can know the scattering amplitude. And once we know the scattering amplitude, of course, we know the differential cross section. So we will take the story up in the next lecture. We will set up the scattering problem and write down the, we'll finish the setup of the scattering problem. And if time permits, we can also look at one or two examples of how to calculate these things.